So hello everyone, my name is Samir, and along with Chung, today we are going to talk about the journey of scaling machine learning with Spark at Facebook. More specifically, this talk is going to focus on feature engineering today, which is the art of extracting and transforming features before they are used to train an ML model. And the purpose of this exercise is to make the model more accurate and stable. So before we start the talk, just a very brief introduction about us. My name is Samir Agarwal. I'm a software engineer at Facebook in the data platform team. I'm an Apache Spark committer where most of my work has been focused on Spark Core and Spark SQL. And previously, I spent many wonderful years at Databricks and at UC Berkeley working on Spark.
I'm Cheng Su, a software engineer at Facebook. Same as Samir, I'm working at the data platform team. I'm a Apache Spark contributor, mostly focused on Spark SQL. Previously, I worked on Hadoop and Hive team at Facebook.
So here is the agenda for this talk. We'll first start off with a brief overview of a typical end-to-end machine learning workflow at Facebook. Then we are going to talk about our logical and physical data layouts that help influence many of our architectural design decisions. After that, we are going to take a deep dive into two important aspects of feature engineering, namely feature reaping and feature injection. And finally, we are going to conclude by sharing some of the problems that we are working on in this space. It shouldn't probably come as a surprise that most Facebook products and services leverage machine learning today. Our newsfeed ranking algorithms help people see the stories that matter to them most. Our ads teams leverage machine learning to determine which ads to display to a user. And machine learning is really at the focal point of several of our search, language translation, and speech recognition algorithms. This figure illustrates how a typical end-to-end machine learning flow looks like at Facebook. An ML engineer starts by first identifying the data source their model will consume. This is typically spread across numerous Hive tables that are often filtered, aggregated, or joined with other tables. Once the data source has been identified, the next step is to add and extract relevant features from this raw data. This is followed by an offline training phase to build the model. And once the model has been built, there is a final inference phase to now run this trained model in production. And this production model is now used for making a set of batched and real-time predictions. The response to these predictions, for example, likes, comments, shares on a particular post, can once again then be logged onto the raw data or in the raw data that's often leveraged to continuously and iteratively improve the quality of our models in production. So in this talk, we are now going to focus on the two left boxes in this flow and specifically talk about one, how this data is laid out logically and physically, and two, how do we leverage these smart data layouts to efficiently add, delete, and extract relevant features from raw data? So talking about data, the Facebook data warehouse currently has exabytes of data that are spread across millions of tables. Specifically, for the feature engineering use cases, we typically have a number of use case specific training tables that are used to store this training data. These tables are typically huge, and it's not uncommon for them to span multiple petabytes of data. In terms of schema, we are looking at about tens or hundreds of columns that are spanning user IDs, ad ID, and more importantly, a set of features that are currently used in training. In this particular example, let's say that we are training on the age, the state, and the country of a user to display them relevant ads. Now, as far as the storage is concerned, we usually store these features as maps with the feature ID as the key and the actual feature as the value. These feature values themselves can be simple data types. For example, they could be ints, doubles, or booleans, or they can even be complex types. For example, they can be maps of maps, or structs, or arrays. Now, in addition to the training tables, we also have a large number of feature tables that are stored or that store all possible attributes or features that we could potentially train on. So in terms of schema, we are looking at something that's very similar to the training table, but they are much smaller. So in some sense, like these feature tables can have tens of columns that constitute these additional feature vectors. As an example, these additional feature vectors here could be gender of the user, the set of things that the user likes or dislikes, and this all can be potentially used for training. So now that we know what training and feature tables are, let's talk about two common sets of operations that can be actually done on this data. First, feature injection is this process of extending base features with new and experimental features to improve model performance. In this example, let's say we have an ML engineer that decides to experiment the impact of using the gender of the user for ad placement. In order to do this, we need to effectively join the gender table with the training table and update the feature map to include this gender information. So one way to intuitively think about this operation is that you are now adding new keys to this map in the training table. Second, feature reaping is this complementary process of removing unnecessary features from the training data in order to achieve better training results, or even to just save storage space. For example, an ML engineer may decide that using state or the user's location to train a model no longer adds value to the quality of the results. And as a result, they may choose to delete or read these features from the underlying table to save storage. Intuitively, you can think of this operation once again as a means of deleting existing keys from a map. So now that we have talked about how this data is laid out in these training tables and these feature tables, let's briefly talk about how this data is physically encoded. At Facebook, we use a fork of Apache ORC as our internal data format. But many of you might also be using Parquet, which behaves very similarly. Now, in order to better understand how do we do these operations efficiently, it will be useful to have a quick recap of what an ORC file actually looks like. An ORC file consists of a group of rows, which is called row data, and they are referred to as stripes. Along with this auxiliary information that can be stored in the file footers. Within each stripe, we have several streams of each columns, and each of these streams can have a different encoding and compression strategy. For instance, integers can be run length encoded, strings could be dictionary encoded, and so on. So now let's see how a feature map or a map is actually stored in the ORC table. By default, the keys and the values in this map are stored in separate streams or columns. For instance, let's consider that we have 3 rows in this table. We have keys K1 and K2, and then we have values V1 and V5 that are spread across all these rows. Now, in this case, each key and the value stream is individually encoded and compressed. This means that when we are trying to read or delete specific keys from the table, we need to read, decompress, and decode the keys and values, which is quite inefficient. To solve this problem, we added a new flattened map encoding in our ORC spec. In a flat map, all these values that correspond to each key are now stored as a separate stream. Therefore, for the table that or the example that we discussed in the last slide, in this specific case, we'll now have 2 streams, one for K1, which has all its values, and the other one for K2, which has all its corresponding values. For those who might be familiar with how structs are encoded, this is actually a very similar concept here. Each struct subfield basically has its own stream in the same way each key in this map has its own stream. Now, due to this, since each key's value stream is now individually encoded and compressed, as a result of this, reading or deleting specific keys from this table now becomes very, very efficient. So let's see how this makes this whole concept of feature reaping efficient. Now, just to recap, feature reaping was this process of removing unnecessary features from the training data. At Facebook, we have a number of high-level feature reaping frameworks that generate these SQL queries, which may be used to reap certain tables, partitions, and the feature IDs in the whole process. Now, for each reaping query, Spark Executor launches a sidecar SQL transform process that uses native C++ binary to do these efficient FlatMap operations. This is on the data path. On the control path, the Spark Executor is now responsible for atomically committing the data to the partition. This allows us to not unnecessarily encode, decode columns or map keys that aren't being touched, which makes it extremely efficient. So talking about performance, here are two cases that we actually evaluated. For case one, we took a training table of 20 petabytes in size that consisted of 1,000 features and reaped 200 features out of it. The solution was 14 times more efficient than reading and rewriting all the data against 20 less one. For case two, we took a training table that was much larger in size. This was 300 petabytes in size and consisted of 10,000 features, so an order of magnitude more features, and we still reaped 200 features out of it. The solution was actually 89 times better than the current baseline. The intuition, once again, is that the complexity of the reaping here depends on the number of features that are being reaped and not the total amount of data in this table. With this, I'll hand it over to Chung, who is next going to talk about feature injection.
Feature injection is another important operation for feature engineering besides the feature reaping we just described. In previous slides, we discussed feature reaping as an efficient solution to delete features, and here we discuss feature injection as an efficient solution to add the features. Okay, let's go back to our previous slides for data layouts. On the left, we have a training data table which contains all the features we use in production, such as age, state, country, etc. The table is pretty big and can contain thousands of several 10,000 features per row. On the other hand, we have multiple feature tables on the right, which collected all different kinds of features every day. Most of them are not included in training table. For example, one machine learning engineer wants to do a training model experiment to figure out whether gender in the feature table is a good feature to be used in production. So one naive way is to join training table and the gender feature together and use the joined output for training. However, this is not acceptable as the training table has very large volume and it takes too much compute and storage source to compute for every features. To make this work in production, we have basically two requirements for the solution. The first one is to allow machine learning training experimentation to be fast as possible. And the second is to save storage space as much as possible. So here we are introducing our solution, align tables. Okay, what is a align table and how it can be efficient? So intuitively, we are storing the output of the join between training table and the feature table into separate row-by-row align table. So an align table is a table that has same layout as original training table in the way that it has same number of files, same file names, same number of rows and row order in each file. Here's a simple example. On the left side, suppose we have a training table and it has two files, file_1.orc and file_2.orc. So each file stores, for example, user ID and corresponding production features. The features can be 1,000 or 10,000, which is pretty large. On the bottom, we have a feature table and it has one file, for example, file1.orc. So it stores the feature we want to do the experiment, F1, F2, F4, etc. for each row. So we join the training table ID and the feature table ID together and generate the align table on the right side, which has the same number of files with the training table you can see, and the same row order in each file. For example, in first file, file1.orc, it has a feature for ID I1, 2, 5, etc. So why this solution is better than drawing training table and the feature table together? So note, we only read the ID column from the training table for the purpose of drawing, which is pretty fast. We do not read or write the production features column from training table at all. So read and writing production feature column has a major compute and storage cost here. And here is the secret sauce that how we generate align table. We add dedicated Spark planner support. An example of Spark physical plan is on the right side. So note, some of the query plan nodes, such as shuffle before the drawing, are skipped here for simplicity. And the light green query nodes are added especially for align table. Let's go over that. After scanning of training table, an actual project operator is ended to annotate the file name and the row order for each row. Then after the drawing, an actual shuffle is ended to shuffle on file name. This is to make sure all the rows with same file name will go to one shuffle partition. And after the shuffle, a local sort on the file name and row order is executed. When writing the table, so we have the rows to be sorted on original row orders, and all the rows of same file are written together. We have talked about how to write the aligned table. Here is how we read the aligned table efficiently. In our fork of ORC, an aligned table row by row merge reader is implemented. The reader reads each aligned table file with the corresponding original training table file in one task. And each task will read row by row according to the row order in the file. And for each row, the corresponding columns will be merged together. As an example here on the left side, reader task 1 will read the file 1 from the training table and align table. And for each row, for example, row with ID 1, 2, and 5, the new feature F1, F2 now will be merged into the training table production features column. Here we give out a performance comparison between our aligned table solution and other two baseline solutions. The first baseline solution is what we described before, which is a left auto join between training table and feature tables, and output will be a materialized training table with new feature ended. The cons of this solution is pretty obvious. For every training experimentation, we need to read and overwrite all the columns of training table. We compared aligned table solution versus the left auto join solution, and we observe quite huge wins there. There's a computer saving to be 15x and the storage saving to be 30x. And the second baseline solution we are comparing with is called local hash join. It works in the way to load feature tables into a distributed hash table. Here we use Laser, which is an internal Facebook distributed hash table service built on top of RocksDB. There's a paper link at the bottom. You can learn more about Laser. And when reading each row from the training table, a local hash join is performed, for example, on the join key ID column to merge the new features from distributed hash map and the production features together. The cons of this solution is that this needs an actual dependency in the system, which is distributed hash table service. It needs several steps, such as loading the hash table and drawing from the hash table. This impacts latency, reliability, and efficiency from time to time. In addition, the local hash join is not free, and this is costly as we need to do the drawing every time when we read in the training table. We compared aligned table solution versus local hash join solution, and we observed 1.5x computer saving and 2x round of storage saving. To recap, we talked about 4 major points in this session. First, we give an overview of machine learning workflow at Facebook. Then we talk about the smart data layouts and encoding we developed for feature engineering at Facebook. Then a feature ripping solution to efficiently remove features, and a feature injection solution to efficiently add features. So for future work in this area, there are 2 directions we are working on. The first one is to provide better Spark SQL interface for machine learning primitives. To recall, for feature ripping, our current SQL interface is SQL transform. And for feature injection, our current SQL interface is a specialized join and insert into aligned table. But we can provide better interface for our ML engineer, such as absurd primitive. Here is an example to merge the certain features into training table, which is much more cleaner and intuitive. The second direction is we are onboarding more and more ML use cases to Spark. Currently, we are focusing on feature engineering, which is data preparation before ML training and inference. And we are working on to onboard batch inference and training use cases to our Spark platform. That's all. And this concludes our talk. Feel free to ask any questions, and your feedback is very important to us. Thank you.